Hello everyone, we are in the module 2 of this course and this is lecture 1. So, today we are going to learn SDOF system. So, our main topic today is how to model it and then how to solve it. So, for that let us first consider a portal frame that very often we encounter in civil engineering. So, we have a frame here as you can see. So, we have two columns, together they provide a lateral stiffness and let us define that stiffness by K, and the slab which has a mass is located at the top. Now, for this system obviously we have only 1 degrees of freedom. So, x of t, which is the lateral deformation in this case, is the only degrees of freedom present, and let us apply a force of f of t. So, in this case again we can idealize this system where we can identify there are some structural elements. In this case it is the column that provides the stiffness in the lateral direction, and then a mass m which actually vibrates the moment we apply a forcing function f. All of them are denoting this frame structure. Now, if we idealize this, we can consider this mass as you can see. So, this is the mass which moves in the lateral direction. So, I provide a roller here and the degrees of freedom you can see it is x of t. Now, then the moment it tries to move in the lateral direction, it experiences a stiffness which is represented by this spring. And then from our experience what we have seen that any structural system that vibrates, after some time it comes back to its equilibrium position at rest. So, that is represented by the damper here. So, for the time being we will not consider a damping here, we will as we progress in this course we will separately consider that, but we have a stiffness K, a mass m, and we apply a force f of t. Because we have only 1 degrees of freedom, we call it SDOF system. Now, for this mass we can draw the free body diagram. So, in this case if I draw a free body diagram, so this is the mass, we apply a force f of t, then the moment this mass tries to move on the right hand side, there will be a forcing function. So, this is the elastic force F e, and this f of t is the applied force, and there will be an inertia force because the moment we try to deform its location by x of t. So, there will be an inertia I. So, these are the 3 forces acting. Now, we can identify what is the inertia force. This is nothing but mass times acceleration, that is if we differentiate x of t twice we get the acceleration and multiply that with the mass we get the inertia force. Then we have elastic force, in this case the stiffness K times the deformation x of t in the horizontal direction. Now, once we identify all these component forces, then we can apply the equilibrium. So, sum of all forces acting in the horizontal direction is equal to 0, because the system is in dynamic equilibrium. And then if we identify all these forces, so we have inertia force plus elastic force, which is equal to applied force. Then if we further substitute the expression of all these forces here, we get m x double dot plus k of x is equal to f of t. So, that is the equation of motion. Obviously, today we have a SDOF system. So, this is the equation of motion for an SDOF system. Now, this is a ordinary differential equation, and our main objective is to find out x of t, right. That is the solution. The moment we can solve x for all t, we get the response of the structure. Now, for that we need some initial conditions. So, at t equal to 0, we have x of 0 is equal to x 0, and then again at t equal to 0, x dot, that is the velocity, is equal to x dot 0. So, these are the two initial conditions, and hence this is called an initial value problem. So, the moment we identify the equation of motion, then our task is to solve this differential equation of motion, and the moment we do that, we can easily identify what should be the response the moment we apply a force f of t. So, for that, let us see how we can solve it. So, we have the equation of motion is m x double dot plus k x is equal to f of t, and the two initial conditions, x 0 of 0 is equal to x subscript 0, and then x dot of 0 is equal to x dot subscript 0. Now, we have a forcing function. The moment we have a forcing function in this ODE, we know how to solve it. So, x of t, that is the total solution, in this case will be the sum of complementary function plus particular integral. How do you get the solution corresponding to complementary function and particular integral? So, what we have to do? We have to first identify the homogeneous part. That means, on the right hand side we have 0. So, this is called free vibration problem, and the moment we identify the forcing function, this is what we call forced vibration. So, first we will consider the free vibration problem, and then gradually we will move over to forced vibration. So, in case of free vibration, we propose a trial solution, in this case x of t. The trial solution is p a to the power lambda t. So, that is the trial solution. So, once we propose a trial solution, our next task is to substitute this expression in the original equation and then see what happens. So, for that what we have to do, we have to express x double dot. So, we find out x dot of t. So, that will be p lambda e to the power lambda t, and then again if we differentiate once more, we get x double dot. So, that is p lambda square e to the power lambda t. So, we have the expressions of displacement, velocity and acceleration, and the moment we have it, then we can substitute it back in the original equation, and then what we get is p lambda square e to the power lambda t plus, there will be an m, plus k times p to the power, p e to the power lambda t equal to 0. Then we can further simplify. So, m times p times e to the power lambda t, then within bracket what we have here is lambda square plus k by m is equal to 0. Now, let us assume omega n square is equal to k by m. I will explain that in a minute. So, if we assume that, then what we get, we can further simplify this m p e to the power lambda t is equal to lambda square plus omega n square. This is equal to 0. Obviously, in this case p e to the power lambda t, that is the trial solution, which is not equal to 0, we are only left with the condition that lambda square plus omega n square is equal to 0. So, the condition we get is lambda square plus omega n square 0. Now, what is omega n? Omega n is called the natural frequency. What does it mean? Recall, we started with a frame. So, it has a stiffness and the mass, and the moment we identify the degrees of freedom, so it is allowed to move in this direction. So, if we just pull it in this direction, so if we pull it in this way and then release it, then what will happen? It will start vibrating in the horizontal direction. In that case, it will vibrate with this natural frequency. So, what is omega n? This is nothing but square root of k by m. Now, once we do that, we get the expression of lambda, and that is equal to plus minus I of omega n. Now, once we find out the expression of lambda, then we can easily write down the expression of x of t, which is, in this case again we are solving complementary function. So, CF will be a e to the power I omega n t plus b e to the power minus I omega n t. So, that gives us the solution for this problem, and then if we further simplify this expression, because if you recall, e to the power I theta is equal to cos theta plus I sin theta. So, if you use this expression, then you can simplify. So, this will be c, a constant, times cos omega n t plus d sin omega n So, what we get is the response of the S-DOF system x of t when there is no forcing function. So, the question is why it will vibrate. Again I draw your attention that we apply some initial condition, and because of this initial conditions there will be vibration. Now, if you look at the solution, we have two unknowns or two constants C and D, and we have two initial conditions. So, the moment we have two initial conditions defined, then we can find out the solution for C and D. So, let us do that. So, we have x of t is equal to C cos omega n t plus D sin omega n t, and we have initial conditions. So, first we differentiate and find out what is x dot of t, and we get minus C omega n sin omega n t plus d omega n cos omega n t. So, once we get these two expression, our task is to satisfy the initial conditions. For that, let us first consider. So, x of 0 will be equal to C times cos omega n times 0 plus d sin omega n times 0. Now, if you do that, obviously this will go to 0 and this is 1. So, what we have here, this is equal to C, and we have the conditions. First initial condition is x naught. So, we get C as x naught. Then our next task is to consider the second equation and use the second initial condition. So, for that we have x dot of 0 is equal to minus C omega n sin omega n times 0 plus d omega n then cos omega n times 0. So, what we get, obviously again in this case this will go to 0 and this is equal to 1. So, we are left with d of omega n, which is equal to x dot naught. So, that is the second condition. So, we have C equal to x naught and d equal to x naught dot divided by omega n. So, these are the two constants, and the solution is x of t is equal to x naught, that is C cos omega n t plus d, which is now x naught dot divided by omega n times sin omega n t. So, that is the solution. Obviously, if we assume x naught is equal to r cos theta and x naught dot by omega n is equal to r sin theta, then using this we can further find out this solution in a more compact form. So, let us see how we can do that. So, if we put this expression back here, what we will get, x of t will be equal to r cos omega n t minus theta. So, what is r? R is equal to square root of x naught square plus x naught dot square by omega n square. So, that is the amplitude. And what is theta? In this case, we know it is tan inverse x naught dot divided by x naught omega n. So, we have the complete solution for the homogeneous part, and if you look at the solution, here is the solution. If you look at the solution and plot it, what we will get? So, this is our x of t, and as time progresses, so we will have a response. At t equal to 0, we have x naught. So, this is our x naught, and then it actually goes like a sinusoid. So, this angle, so if you draw the tangent here, so this angle is x naught dot. Now, obviously, what is the amplitude? So, if I consider peak to peak, so this is the time period and this is the amplitude r. So, this is time period and we get the amplitude. The point to be noted here, as the time progresses, then we have the response also following this sinusoids and it continues. It never comes back. The reason is we have no damping force in the equation of motion. We will consider that, but for the time being, when we have undamped free vibration, so this is undamped free vibration, our solution follows this expression, and as time progresses, it will go towards infinity with the same amplitude and time period. Now, let us consider an example. So, just imagine we have a mass which is hanged by a spring. So, we have this mass, spring constant is k, and this is with a weight W. If we divide this weight, we will get the mass, and then from this position, so this is initial position, then we release it. Obviously, due to gravity, it will come to a static equilibrium position. So, what is this deformation? This is say static deformation, we call it YST, static. We can easily quantify this deformation. So, if the stiffness is K and this weight W, because of this weight W which is acting vertically downward, this body moves from the initial position. So, if I mark it say position 1, then it goes to position 2. Now, once it reaches position 2, what happens? At this location, it will try to vibrate. Then for that, let it deforms by an amount of y. So, this is also a Esdorf system. But in this case, we have a static deformation, and then on top of static deformation, we have a dynamic component. Now, if I plot the response, so this is t and the response in this case y of t. So, we have a static deformation. So, this is the static deformation, and about this deformation it will start vibrating. The question is, in this case, how can we develop the equation of motion? So, let us consider the body here at the static equilibrium position, and from there it moves in the vertical direction. So, the degrees of freedom is y in this case. Now, let us draw the free body diagram. So, isolate the body. In this case, the gravity is acting downward, and for that we have this weight W. Then at this point at CG, there will be a inertia force, and in this case it is mass times the deformation, dynamic deformation, that is y, double dot of y times mass is the inertia force. And then there will be a spring force also, that is K times y st plus y. Now, the moment we identify all the components, again in this case summation f of y will be equal to 0. So, if that is the condition, then we can write down the equation of motion. So, in this case my double dot plus k times y of st plus y is equal to w. Obviously, we can open this bracket. So, what we will get m y double dot plus k times y of st plus k times y is equal to w. Now, remember k times y of st, this is actually the force acting here. So, k times y of st is equal to w. So, we can substitute that, and if we do that, we get w here. Obviously, this w and this w on the right hand side will get cancelled. So, we will have the equation of motion my double dot plus ky is equal to 0. So, that is the equation of motion in this case. We can further simplify it. So, we will have y double dot plus k by m, which is omega n square times y is equal to 0. Now, what is omega n square? It is nothing but k divided by m. So, we can replace m in terms of w. So, w divided by g, gravitational acceleration. So, we will get here k times g divided by w is the omega n square. So, natural frequency in this case omega n is square root of k times g divided by w. So, if we consider some values, so w is equal to say 200 Newton, and then stiffness of the spring K is equal to say 4 Newton per millimeter. In that case, we can actually find out the solution. So, in that case, we have 4 times g, acceleration due to gravity is 9810 millimeter per second square. So, we have here 9810 divided by w, which is 200 square root of this. If we solve this, we will get the value of natural frequency in this case 14.01 radian per second. So, what we get? Our equation of motion in this case my double dot plus ky equal to 0, omega n square is equal to k by m, and the nature of the solution, that is so obviously we can identify the time period t, and t is equal to 2 pi by omega n, and we can also write this expression as 2 pi f, where f is equal to 1 by omega n. So, f is also the frequency, it is in unit hertz. So, let us consider a different example. So, example 2. So, in this case we have a simply supported beam, and we have a mass m placed at the middle. Now, if we suddenly apply this mass, obviously beam will vibrate. So, it will deform this way, and then it will go the other way, because vibration occurs in both positive and negative direction. So, it will move this way, go down and up, and because there is no damping for the time being, it will keep on vibrating. Now, the length of this beam is L, and its flexural rigidity is given by EI. Now, this beam we can idealize as a mass spring dashpot. For the time being, we do not have any damper, so there is no dashpot. What we have here is the mass m hanging from this spring whose stiffness is K. Obviously, this simply supported beam is idealized by this spring, linear spring with spring stiffness K. Now, we can quantify this spring stiffness. So, for that, if the central deformation here, say if this is delta, so the central deformation delta is nothing but P L cube divided by 48 EI. Now, what is the definition of stiffness? It is the force required for unit deformation. So, if we have a force P causing a deformation of delta, so it is P by delta. Now, the moment we do that, we get K, that is the spring constant, is P divided by PL cube, then 48 EI. Obviously, this is equal to 48 EI divided by L cube. So, that is the spring stiffness. So, let us identify the spring stiffness. So, this is equal to 48 EI divided by L cube. Now, if we find out what is omega n, this is square root of K divided by m. So, we know the expression for spring constant, then we can find out what is the expression for omega n in this case. So, it will be 48 EI divided by m times L cube. So, that is the omega n, and with this omega n, the beam will vibrate in the vertical direction. So, the moment we apply this mass at the midpoint of the beam, it will start vibrating with this frequency. And what will be the response is y of t in the vertical direction. So, y of t will be equal to r cos omega n t minus theta. So, that is the complementary function. So, we have solved undamped free vibration. So, with that, let us close here. In our next class, we will continue on this topic and we will see how we can consider damping and then what are the other characteristics of natural frequency, how it affects the solution. That will go through in the next class. Thank you very much.